Okay. I want to hit number one. This came up first hour, and I think this is beneficial to have a conversation about. Okay, number one and two. Okay, so if you have 18 volts here, the your voltage gain. So you need to make it. I guess the important thing is making a distinction between your total and your individual. Okay. So here we have a 18 volt gain, and because there's only one resistor, we have an 18 volt drop. There we go with that. Simple circuit. Now, if we add another resistor in series, what that does is that causes, okay, the total voltage, this is determined by your battery, by your power supply. Whatever your power supply is, that defines your total voltage. Okay. Now, when we add another resistor in series, what does that do to our total resistance? Makes it goes up, okay? And our total current therefore goes down because the total voltage, unless you change the battery, you're not changing your voltage, your total voltage. Okay? Now, what that does though, however, to the individual, that's another story. So what that does is we have not changed the ladder. The ladder is still the same height. But now we need to divide that 18 volts among both resistors. Just saying that these are the same resistance. Keep the conversation easy. You have a 9 volt drop here, slide, and you have a 9 volt drop slide there. So that the total gain, voltage gain equals the total voltage drop. Does that make sense? Okay. And that is due to the fact that the total resistance, the total current went down, causing the total voltage to go down in an individual. Okay, if we added a third, if this is identical, you'd have to go 6 volts, 6 volts, 6 volts. Does that make sense? Okay. Versus in parallel, you still have an 18 volt gain that has not changed. So you have an 18 volt slide drop. Okay. If we added another one in parallel, the voltage, total voltage, is the individual because each one's independently hooked up. And so you have another slide of 18 volt drop because you've got one loop, two loops. Voltage gain equals voltage drop. Okay. And as you add another resistor in parallel, what happens to the total resistance? Goes up or goes down in parallel? Goes down. So the total current goes up. Good with that? So I just wanted to work through that a little bit. Okay. Questions there? Okay. You see why I'm recommending, highly recommending that you redraw your circuits. Gives you a path back. If you don't do that, well, I guess that's up to you. I'm just letting you know it's beneficial. Okay. So one question I wanted to touch on. If you're following along, this is way back in lesson 3. Thumbs up when you have a guess. Correct answer is D. Dangerous dinosaurs. These batteries are hooked up in series. I recognize that we don't have flashlights like these anymore, but when you load batteries in something, there's a specific arrangement of your batteries, right? Like you gotta get the pluses and the minuses in the right arrangement. Okay, that is because your battery pack is wired in series. Does that make sense? Okay. What you're doing here is you're causing two ladders. You have a 1.5 volt gain, and then you have another 1.5 volt gain, giving you a total of 3-volt drop. Does that make sense? Okay. So all AAA, AA, C, D batteries all have 1.5 volts. Okay. This device would require how much volts? How many volt? What's the voltage this requires? 6 volts. Does that make sense? If you flip flop one of those, that's like having an upside down ladder. Not going to help you attain that voltage. Good with that? Okay. So just trying to make connections with life here. We all deal with batteries. They're wired in series. Okay. All right. I've got some good challenging questions here for you. Give you a hint. Multiple steps are required. But the difference is I'm giving you the current through an individual resistor, not from the battery. This will be a different strategy, but you're using the same concepts. Thumbs up when you have a guess. Keep thinking. I got a third of the people with thumbs up, so keep thinking. Have a conversation.
Find the total current of the parallel voltage, and then that was on it, or like
So also like parallel, that's the same one. 6 is parallel. And add parallel.
All right. Ready? All right. So, it's a different strategy. I'm given the current going through this one. I know the resistance. What can I find for this resistor? Voltage. Okay. So I've got 12 volts here. Yes? Okay. The 6 and the 3 are wired how? Parallel. What measurement is the same in parallel? What? Wait a minute. We just. Oh. You see how we're like. Oh. And wait a minute. I've got. What else can I find here? Current. Right? So I got 4 amps here. Okay. Yes? Are we seeing the the logic train here? Okay. Now, these two would be wired in series with 4. We'd simplify these two, right? Okay. And we would redraw this like this, right? Like we would do, there's 4, and then this would be, I think it's 2, and ends up being whatever, okay? We draw these two like that, okay? These are in series, so we know that what's the same in series? Current, okay? How much is going through this one? Well, at this junction, there's 2 amps going through that one, and 4 amps going through this one. Therefore, how many has to be going in? 6 amps, and that's what's going through the 4. Okay. D, dangerous dinosaurs. Good with that? Where did I got it. There it is. Try that one on for size. Have a conversation.
Why am I getting cross?
Correct answer is? Correct answer is 2. Okay? All of the current is going through A and splits B and CD. This this branch has less resistance than this one does. So more goes through B. Whatever goes through C has to go through D because these are in series with each other, but there's less, because there's more resistance in this branch, less current goes through it. Good? Okay, these last 2 questions, these are challenging. Please consider the hint. Consider the hint.
Stop influencing my answer.
Think in your brain. Have a conversation.
Don't put on speaker. I don't care what you
All right, what do you say? Not C. Here we go. Ready? Okay. The 2 and 3 are wired how? Parallel. Okay, check this out. Ready? If I added a resistor in parallel, what happens to the total resistance? If I added a resistor in parallel, what happens to the total resistance? Decreases. Yes, in parallel. I'm adding another checkout line to Walmart. So if I take one away that was in parallel, bless you, that increases the resistance. Yes? Okay? That increases the resistance. And because this is in series with that, the total resistance increases. I would redraw this like this. Right? This would be 2, 3, and this would be 1. Right? I'd boil this down. Okay? If I take away 2, that's going to make the resistance of this guy go up. This is in series with this, so the total resistance of the circuit also goes up. So the total current goes down, and it makes it dimmer. Okay? I don't, listen. Just because you get the right answer doesn't mean a whole lot. The thinking, the thought process is what means stuff. Because I'm not going to give you this question. I'm going to give you something else. And you're not just dodging bullets, you're trying to be bulletproof. Whoa. Okay? Does that make sense? Okay? Last question. Last question. Consider the hint.
No.
30 seconds.
No, because also
Ready? Answering with Ohm's law for this guy falls apart because we don't know what happens to the current. The total current decreased, yes, 100%. But you could be arguing, well, some of it went to 2 and now it's all going through 3. You don't know, it's fuzzy. So whenever it's fuzzy like that, that's when we incorporate Kirchhoff's loop rule or junction rule. Okay? The loop rule says voltage gain equals the voltage drops. Okay? The voltage drop across this one did what? Resistance stayed the same, current went down. What happened to the voltage? Decreased. So, in order to keep 12 volts ladder and we decrease the slide height, what has to happen to this? Has to go up. So the voltage here has to go up because of Kirchhoff's loop rule and gets brighter. Gets brighter. Got a worksheet due tomorrow.